To display three-dimensional graphics, we must only show the visible surfaces, or alternatively, we need to do hidden surface removal. We want to see only those surfaces that are in front of our camera, the ones that occlude other surfaces. For example, in this case, A should be fully visible, whereas only this part of B should be visible, and only this part of C should be visible. Parts of B that are behind A and parts of C that are behind A should not be visible. OpenGL uses a hidden surface removal method called the Z-buffer algorithm, which saves the depth information of fragments as they are rendered so that only the front fragments appear in the image. So how does the Z-buffer algorithm work? This algorithm is the most widely used hidden surface removal algorithm and has the advantages of being easy to implement in either hardware or software. It is compatible with the pipeline architecture of OpenGL, where the algorithm can be executed at the speed at which fragments are passed through the pipeline. The algorithm works in the image space. However, it loops over the polygons rather than over pixels of the frame buffer. So here we have an example of two polygons, the triangle and the square, where the triangle is denoted by B and the square by A. We can compute a color for each point of intersection, say point P, between a ray from the camera's center of projection and a pixel. We must check whether P is visible. It is visible if it is the closest point of intersection to the camera. So if we move the ray of light like this, or the ray from the camera like this, if polygon B intersects this ray first, it is visible. If we are rasterizing polygon B, then its shade will appear at the pixel on the screen where Z2, where its depth is less than Z1, the depth of A. Z2 is the depth of B polygon and Z1 is the depth of A polygon. So if Z2 is closer or Z2 is smaller than Z1, the shade of B would appear at that particular point or pixel. If we are rasterizing polygon A, then its shade will not appear at this point because it is behind the polygon B. Let's look at a pseudocode of the Z-buffer algorithm. First, we initialize the Z-buffer with the furthest values and the frame buffer with the background color. Note that the Z-buffer has exactly the same size as the frame buffer. Next, we loop through each polygon one at a time. And for every polygon, we rasterize the pixels inside that polygon and compute the depth, the Z value for that pixel, and the shade of that polygon that would be at that pixel location ij. And if this Z value is greater than the Z buffer current value at position ij, we assign this new Z value to the Z buffer. And we also assign this new shade to the frame buffer at the same location ij. So once we loop through all these polygons, at the end of this algorithm, the shades left in the frame buffer would be the ones that are closer to our camera and the ones that should be visible. In OpenGL, Z-buffer algorithm is implemented using these functions. In the main function, we use glut init display mode to request for a glut depth buffer in addition to the RGB buffer. We also use the enable command to enable the depth test. This is where we tell OpenGL that it should perform depth test. Then we clear our buffers using the GL clear command. We clear the color buffers as well as the depth buffers. This is how the output of the Sierpinski gasket code looks like in OpenGL if we give the same color to all the tetrahedra. And notice that only the surfaces that are closer to us are visible and they are hiding the ones that are occluded by these surfaces. Another less popular algorithm for hidden surface removal is the painter's algorithm. Although image space methods such as the Z-buffer are more popular due to their ease of implementation, often object space methods such as the painter's algorithm are used in combination. The painter's algorithm is an object space approach to hidden surface removal. It is one of the simplest solutions to the visibility problem in 3D graphics. The name painter's algorithm refers to the technique employed by many painters of painting distant parts of a scene before parts which are closer, thereby covering some areas of the distant parts. The algorithm sorts all the polygons in a scene by their depths. Polygons are painted from the furthest to the closest, so that when a closer polygon is painted, it is painted over the furthest one. Because of how the algorithm works, it is also known as the depth sort algorithm. While the painter's algorithm is simple, it has a problem. Suppose that we have the Z extent of 5 polygons, A, B, C, D, E. Polygon A can be painted first because it is the furthest from the camera. Center of projection is somewhere here. However, we cannot determine the order of the painting of all other polygons because their depth extents intersect each other. Hence, the algorithm needs to run a number of increasingly more difficult tests in order to find the painting ordering. The simplest test is to check the X and Y extents of the polygons. If either of the X or Y extents do not overlap, neither polygon can obscure the other, so they can be painted in any order. If the above test fails, we can still determine the order of painting by testing if one polygon lies completely on one side of the other. The painter's algorithm fails in two cases. Suppose we have triangles that pierce each other, intersect each other. Now, it doesn't matter which triangle you draw first and which ones you draw later, you cannot achieve a correct drawing like this. The painter's algorithm will also fail if you have overlapping triangles like this in a cyclic order. So it doesn't matter which triangle you paint first, you can never achieve this correct shading of the polygons.